Okay, so in this video, we'll consider another application of the determinant. And this application is called Cramer's rule. And as we'll see, we can use determinants to actually solve for a linear system. So here's the assumptions. We assume we have a square matrix A, so A is an n by n matrix, where the determinant of A is assumed to be non-zero, right? And if you remember, the fact that the determinant of A is not zero implies that A is an invertible matrix. Consider now a square linear system where the matrix A is the matrix of coefficients of the linear system. So we consider a system in the form A x equals b, where of course A is the matrix of coefficients, x will be the vector of variables. Since we have an n by n matrix of coefficients, this means we have n variables. So let's list them as x1, x2, up to the nth variable xn. And b, of course, is the column vector of constants. So we can write b as b1, b2, up to bn. We know that if the determinant of A is invertible, if the determinant of A is not zero, the matrix A is invertible, and we know by consequence that the system has a unique solution. If we multiply on the left of both sides by A inverse, the unique solution vector x is given by the inverse of A times the column vector b. So we can solve the system using the inverse of A. We can also solve the system the old-fashioned way by simply building the augmented matrix, where A is the matrix of coefficients, B is the column of constants, and of course labeling our columns for the variables. And that is yet another way of solving for the linear system. So as this stands, we have two ways of solving for the system. Augment A with B, so construct the augmented matrix of the linear system, row reduce, and because A is invertible, we'll have a unique solution. Or use A inverse times B to give you the unique solution vector, hence the unique solution for each variable for x1, x2 up to xn. What Cramer's rule gives you is a way to solve for the variables independently. See, if you use this method, you simultaneously find the values of all the variables. Same for the row reduction. Once you row reduce fully, and then use backward substitution, you'll solve for all n variables. The nice thing about Cramer's rule is it gives you a way to solve for a single variable without solving for the others. And here's what Cramer's rule says. So we'll have the same assumption. A is a square matrix. It is the matrix of coefficients. And the determinant is not zero. Suppose you want to solve for only one of the variables. Say the ith one. So xi. Maybe I is 7. And you only care about the value of x7 and not the other values. Well, Cramer's rule gives you a way to solve for xi without knowing or without having to solve for any of the other variables. And the result is simply the determinant of ai, and we'll define this in a second, over the determinant of the coefficient matrix. And this is true for any given variable. So for any given I between 1 and n, therefore for any variable. The only question here is, well, what is ai? How do we construct it? We already have A from the beginning. How do we construct ai? So quite simply, ai is obtained from A and we tweak A a little bit. So ai is obtained from A by replacing the ith column by, quite simply, the column of constants, by b. And that's it. That's Cramer's rule. You want the ith variable, replace in the matrix A the ith column by B, the column of constants, find the determinant of this matrix over the determinant of the original matrix of coefficients, and you have solved for the ith variable. Let us now consider a very simple example where we have a 2 by 2 linear system. Suppose we're asked to solve for the system 5x plus y equals -1 and 3x plus 2y equals +4. Right? We know we can solve for the system using row reduction. We can also rewrite the system in matrix form as 5, 1, 3, 2 times the vector of variables x, y equals the vector of constants -1, 4. So this is your A. This is your uppercase X, the vector of variables. And this is your uppercase B, the column vector of constants. So we could solve for the system using row reduction. We could invert A and solve for the vector of variables this way. Let us now use Cramer's rule. So let's solve for x first. And you'll see we will obtain x independently of y. Well, x equals. Well, if you go back to Cramer's rule, well, what is I here? Well, I is the index of the variable. If I is 1, you have the first variable. If I is 2, the second variable, and so forth. So here, x is the first variable, so x is simply x1. And now we use Cramer's rule. x1 is the determinant of a1 over the determinant of a. Well, determinant of A, this is a 2 by 2 matrix. So we have determinant of the matrix 5, 1, 3, 2. On top we have the determinant of A1. Well, this will also be a 2 by 2 determinant. And now, well, how do we obtain AI? It is obtained from A by replacing the ith column by B. So here we take A, but we replace its first column, 5, 3, by B, -1, 4. And we keep everything else the same. So replace the first column of A by the column B, but leave everything else the same. And now we have quite simply the ratio of 2 by 2 determinants, so AD minus BC in both cases. So what do we have on top? -2, -4, -6, over 10 minus 3, +7. And there you have it. X is equal to -6 over 7. And we have no idea what y is, and that's the nice thing about Cramer's rule. It allows you to solve for a variable independently of the other variables. Let us now solve for y. Well, y is the second variable, so it equals x2. And x2 is quite simply the determinant of a2 over the determinant of a. Now we already found the determinant of a. It's equal to 7. So don't do that again. It's over 7. Determinant now of a2. Well, how do we obtain a2? We take the matrix A and replace its second column, so replace this column, by once again B. So the column 1, 2 is now replaced by -1, 4. And everything else stays the same, so the first column 5, 3 stays 5, 3. 2 by 2 determinant, so AD minus BC, 20 minus -3, 20 plus 3 is 23 over 7. And there you have it. Y is 23 over 7, x is -6 over 7. We now have found the unique solution to the linear system. And you can check that this is indeed the solution if you simply replace 5x, -30 over 7, plus y plus 23. Negative 30 plus 23 is negative 7. Over 7 is negative 1. Check. 3x, negative 18, plus 2y plus 46. 46 minus 18, that's 28. 28 over 7 is positive 4. So indeed, we have the correct solution. Now, it is worth mentioning that Cramer's rule is nice, but at the same time, it's not so nice. The reason it is nice is it allows you to solve for a single variable independently of the other variables. But if you think about this, to solve for the variable xi, you have to compute two determinants. It's not much work when you have a 2 by 2 system. But if you had, say, a 3 by 3 linear system, you would have here determinants of 3 by 3 matrices, and that's a lot more work. If you had a 4 by 4 linear system, you'd have 4 by 4 determinants. So if you want the complete solution set of a linear system, Cramer's rule is a bad idea, because the determinants are a lot of work to compute, so you're much better off with row reduction. On the other hand, if you want a single value of a linear system, Cramer's rule gives you a really efficient way of finding that value, especially when you have a small system, as in this case, we had a 2 by 2 system. So Cramer's rule was actually very nice. One last comment is, you see, even though at the very end, we had a fraction over 7, nowhere in the calculations did we have to handle fractions. They just pop up at the end. And that's one nice property of Cramer's rule. If your system consists of integer values, you'll never have to deal with fractions, even though at the very end, the answer may be including fractions. And that is Cramer's rule.